Welcome back to another HVAC-Engineering-Techie training video. Today's video is on the technical commissioning process of commissioning control systems. Now, the control system information is actually kind of sprinkled through all the other videos, but this one goes into a little bit more depth on actually how it's commissioned for a control system and what things are different for a control system than a regular HVAC system. And also, by control systems, we mean HVAC control system, electrical control systems, and process control systems. Anything that's got a control system is always commissioned this way. So hopefully that'll be helpful to you. Remember, this channel is the one that talks all things HVAC, engineering design, construction, equipment, systems, test and balance, controls, efficiency, and performance. So before we get started, I'd like to ask you a favor, and that's to become a subscribing member by hitting the subscribe button down below. Give me a thumbs up if you like the video. These are totally free to you, cost you nothing. They're painless for you, but they're really important for me because Google uses those to evaluate these videos, which keeps me on the air. So I'd appreciate it. Let's get started with the video. All right, so the commissioning training videos. All of these videos are based upon the ANSI NEB Standard 110. Which is a standard technical process of commissioning. So it's no big deal. That's just the outline process. The other important videos that we have in here, of course, is Cx-1, which is a whole process. Cx-2, technical site inspection. Cx-3, HVAC pre-functional test. Cx-4, commissioning point-to-point test. Cx-5, HV functional testing. Cx-6, commissioning and test and balance. 7, HVAC control system commission. And 8, HVAC continuous performance tracking systems. These are the basic HVAC commissioning videos. So this gives you a list of what they actually are. So what's the difference? Say if Process CX provides commissioning management to the contractor on site in an effort to deliver a better performing building. It's a good process. Technical CX also provides commissioning management. It adds independent third-party testing of systems to ensure system operability and performance. Process utilizes sampling strategies to lower the cost of commissioning services. Sampling has contractors test only a small percentage of control systems and uses statistical analysis to judge the total functionality of the system. Now, when I first encountered sampling, because I didn't understand what sampling was, and the statistical analysis sounded impressive, so I dived into statistical analysis. At the end of the day, what I discovered by studying statistics, which is a god-awful subject, I do not like statistics because it's actually complicated. Well, what I found out is the engineers who are promoting sampling and use this term statistical analysis basically scared off the other engineers. They never checked it. Well, what you do is when you go to a site and you have a customer who says, well, I don't want to pay for this, so we need to make it a lot cheaper, you could use sampling. Well, sampling test and balance actually works, but sampling controls does not. Having been a control contractor for most of my career, I can tell you that there's many reasons why things don't get done perfect in control world, and you actually need to check these points. So if an owner says, I want you to do sampling, you need to ask the question, what failure rate is okay to you? And they say, well, none. I said, then we can't use sampling. Because sampling is based on the statistical analysis based upon a certain percentage of failure. So if you say, okay, I'm okay with 10% not working, we can sample. We can figure out how to do that through the statistical analysis. But sampling and a statistical analysis does never give you 0 failures, so you can't use it. And it's not a good thing. Owners get that immediately. You don't have to argue with the owner about that. If they really want a building to work, they don't want any sampling. Technical provides third-party testing of 100% of the control points and 100% functional testing of control sequences. Now, a lot of jobs, when I send a crew out to do a commissioning of a control system, with the technicians go, what are you doing? They said, well, we're going to test them. You're going to test all the points? Yes. Oh, my, that's never been done. Yes, it has. So you can see that, unfortunately, the commissioning industry is somewhat turmoil by people not wanting to do the total job, so they're not doing it. Okay, control commissioning activities prior to project design. So what are the contract and responsibilities? So when you actually get a contract, you need to make sure, as a control system, what part does the owner forces provide during the control system design phase? Are they going to review the design? Are they going to sequence a control workshop? Are they going to attend that? And I'll explain what that is later. So, what does the owner want to be involved in? If he doesn't want to be involved in any of that, then basically he's not involved in the design at all, which is possible. What part does the owner force to provide during the control system testing? Assist with the point-to-point testing, assist with the sequence of control functional testing, and functional testing. Now, this is not in the spec anywhere because the owner's he's the one getting the benefit. But it's really the best if you can get his operators involved in doing a point-to-point test or doing functional testing. It is such a major training event for them. It trains them on the system, how this system works, how it's been programmed, and how it works. It's so valuable. Unfortunately, most of the time, those people can't carve out enough time to help you. If you can, it's the best. Number one, it's great marketing services to the customer, but two, it's very productive for them. It also helps you by reducing your labor somewhat, not a lot, and you may have to do some training to help them. What is the most important to the owner for the control system performance? What does he care about? If he doesn't care about anything except, just make sure the building's temperature is okay, then it's not a very rigorous deal. But maybe he's got a building that's very, very important to him, and he wants to see exactly how this works, so he would want to be involved in the functional testing of that space. The owner needs to describe his staff's needs for control system operational programming training. Now, in the construction world, the specifications include in it some specs for training. Unfortunately, those specifications almost never represent what the owner actually needs. Every owner's staff is different. They may have some absolutely control expert working in their staff, and they need very little actual training. True, most of the time it's not the case. Most of the time they have zero control expertise and need lots and lots of training. So you need to make sure that the owner has put in the spec what he actually wants and not just what normally it says, provide 8 hours training. Okay, what kind of training? On what exactly? Do you want to just sit in a classroom and discuss the system? What do you want to do? So the training spec needs to be more structured so you get what you want. Owner needs to describe his desire for ongoing support for the control contractor. What does he want after everybody else is gone? And that needs to be in the specification. The owner's project requirements. Now, that's a document that the owner is supposed to create that tells the contractors what he wants. The OPAR is created by the owner and describes what he expects the construction document to do. HVAC systems and components should be in the OPR. DDC control system and components should be in the OPR. Now, this OPR I'm talking about here is just for the control system. There's a whole bunch of OPR requirements in the other sections, but this is just for the control systems. DDC control approved manufacturers. DDC controls approved system component models. Now, why is that important? Well, normally an owner, especially if he's an owner with lots of buildings, he will have a preference for system type. And the reason is he don't have to retrain his people. His people already know a system. They know how to do that. The problem is if you're sole sourcing a manufacturer, you're going to pay more. It's just the way it is. So they may have it limited to 2 or 3 contractors, but hopefully just 1 or 2. More than 2 becomes somewhat of a problem. So basically that's what they're doing there. Approve control sequence of operation. Make sure that's correct. Control systems sophistication and complexity. You may have an owner that knows exactly what sequences he wants. That's very rare, but you might actually find that. Control system sophistication and complexity. How complicated a system does he want? I've had jobs that are actually based in remote areas where their staff is not a highly technical staff. They just don't have technical people out there. And those systems need to be simple or else they will destroy the system. If you put a complex system where there is no complex staff, technical staff to operate it, it will not function. So you need to make sure the system is designed at the level of the operators. Network system and connectivity. What kind of network do we have in the building, and where do we plan on connecting the control system to it? Control system integration with. What is it integrated with? Is it going to integrate with a fire alarm, security systems, lighting systems, electric power data management systems, vertical transportation, data diagnostics, and dashboard systems? what do you want it to integrate with? We don't want the control contractor to figure that out. We want to make sure the OPR clearly defines what the owner wants. Operations and maintenance training requirements, what we talked about before. Control system and component warranties and guarantees. It's important to know what are the warranties for the system. Control commissioning activities during project design. Create the control system commissioning plan, of course, and it's just a part of the main commissioning plan, but it may have some specifics for the control system. Assemble the control system commissioning team. HVAC design review to understand the system. So if you're going to be commissioning a control system, you need to understand the system it's controlling, or else you can't do a good job of that. Design review for all systems integrated into the control systems. So if you have a control system that's integrating into the elevators, you need to understand how the elevator is going to use that data and how you're going to react to it. Now, the reason they do that, of course, is sometimes they have security access cards, and when you use that card at the entrance to the door of the building, it allows you access for that elevator to the floor you should be going to. And those are in some secure buildings. So it's very common to do it. And also then it can turn on the lights, turn on the HVAC, do everything you need to do for that card access. Control system design review. Commissioning of control system requires more due diligence than other systems because the design is a performance design and not a prescriptive design. So all control submittals are basically design build. Now, why do I say that? Well, remember that it's impossible for an engineer to know the intricacies of all systems that are manufactured. He does not know. He knows what the system he wants it to do, so he puts that in the spec. I want it to control this air handler. I want it to do this. I want it to be a VAV air handler. And that's a performance-based spec. And so he's telling you that this is how I want the control system to work. Mr. Control Contractor, you design a system that does exactly that. And if there's things that actually has to change to make that happen, I expect you to do that. So that's why they're basically design build. So you want a control design review is done at submittal stage. So like a regular HVAC system is not. It's actually done at the design development stage, or so it's done as they're designing it. A control system is not designed until a vendor is selected, so it's done during the submittal stage. Design review of systems architecture, that's the main thing, has it laid out. That's one thing. Design review of network controllers and digital controllers. How are we integrating to a network? Are we using a wide area network? Are we using a local network? What are we using there? Design review of input sensors and control devices, the actual devices and controllers. Design review of control panel layouts and construction details. This is kind of important. Design review of network cable and routing. Design review of control power and UPS requirements. Design review of valves and dampers, types, sizes, and actuators. Design review of systems man-machine interface, types and locations. What kind of front ends do we have? How many of them? Where are they at? Design review of integration controllers for each integration systems. So, there are some common, like BACnet, to do some integration, but normally for fire alarm and systems like that, we will have an integration device. A general review of each controller sequence of operation for general compliance and specification. That's a design review option. Now, why is this the hard part? Well, the way it's intended to work is the designer will publish in the design a submittal of a sequence of operation. And that's supposed to be how the controls are supposed to be programmed and work. Then the control contractor is supposed to take those, rewrite them so they'll work in his system and include all the things the designer did not. There's a whole bunch of things the designer doesn't put in a sequence of ops. He's writing the sequence of ops in English language. Programmers don't program in English language. They have to have entrance points, exit points, timing, type of loop, a whole bunch of things in there that the designer doesn't need to put in there. But and so that sequence for the control contractor should come back in his submittal, but it doesn't actually work that way. What happens is the control contractors photocopy the sequence out of the design and just paste it into their submittal. They don't make any changes at all. And the reason is because they're afraid the designer will disqualify their submittal, turn down their submittal because it doesn't match their sequence. Well, this causes you a problem because they're not going to program what they put in their submittal. They're going to program what they have to do to try to make that, but many times they won't match at all. So that's a problem because you cannot commission what you cannot understand. So basically that needs to be done differently. So you need to redo that sequence of operation, and if he's done what I just told you, you just poke 100 holes in the sequence and send it back for a review during the submittal review and say this needs to be corrected. And then eventually he'll get used to it. And normally we try to have a sequence workshop, which we'll talk about in a little bit here. Standard controlled submittal drawings. Okay, so here's a layout drawing. Now they'll look all different, but this is the information we're trying to gather. This is basically the network. This is the network controller down here. And this is all the individual controllers up here. And this is how the networks are going to look. We'll have 3 branches, 3 sub-networks, and we'll have a main network. This could be going to other networks. And I have a man-machine interface up here. This is a standard controlled submittal drawing. This is central plant. So this is I assume this is chill water system. So this is chiller. Now, a lot of them will look a lot different here, but it has all the devices they're going to use. They'll also have a bill of materials on here to tell you what each device is. You can check all that. Then we'll see here. Here's the other side, the condenser side of that chill water system. It also shows all the different things they're going to control in this. And you need to review these because they need to match the design intent. This happens to be an air handler. Now this is an air handler showing the devices on this particular type of air handler. This is the controller wiring diagram for that air handler. It shows all the inputs and outputs of that controller. It shows the different devices, has a bill of materials, and may actually have a sequence of operation here, may not. May have a separate sequence of operations you need to review. And like I said, this is probably the one they've copied directly, but it may have not actually copied it directly, but they didn't put any details in there that you might need. This happens to be a one page. This is an exhaust fan and has a controller for the exhaust fan, the bill of materials, all on one page. This is a VAV box, shows you what a VAV box looks like and what its wiring is and what the bill of materials is. This happens to be a standard submittal drawings for front panel. Now you can also have drawings that show a lot more detail of a panel, which I'll show you in a little bit. Okay, review the control specifications. Control specifications must be included for each component or control system required for the OPR. So standard control specifications, section 23800, which is the commissioning of HVAC. Standard control specifications for section 23 are 09, instruments and controls for HVAC, 913, instruments and control devices, 913.13, actuators and operators, 913.23, sensors and transmitters, 913.33, control valves, 913.43, control dampers, 923, direct digital control system, 933, electric and electronic control system for HVAC, 943, pneumatic control system for HVAC, 953, automatic, pneumatic, and electric control system for HVAC, 993, sequence of operations for HVAC controls. Now, sometimes the designer doesn't use a sequence in the spec. He puts it on the drawings. Doesn't really matter either place. Just make sure he has one. If he doesn't have them on the drawings or a spec, you got to figure out why, because that ain't going to work. Standard control integration specification. So section 25,000 is actually a control of integrated systems, and this is a spec you need to always check. So operation and maintenance integration is 100. 500 is common work results for integrated automation. 600 schedule for integration automation. 800 commissioning of integrated automation. Now, remember, there can be a problem here is that on many jobs, the division 25,000 is a different contractor than the 23,000 specification, 23,900 spec. So you may have a control contractor just doing the 23 section installing the system, and then you have another contractor that's going to come in and integrate that system either into a master system or integrate other systems into it. So that's why it's important to make sure these specs are clear between each other. And many times they're the same contractor, which is easier. 1,100 is integrated automated network devices, 1,200 integrated automated network gateways, 1,300 integrated automated control monitoring network, 1,400 integrated automated local control units, 1,500 integrated automation software, 3,000 integrated automation instruments and terminal devices, 3,100 integrated automatic instrumentation terminal devices for facility equipment, integrated automation instrumentation and terminal devices for conveying equipment, 3,300 integration automation instrumentation and terminal devices for fire suppression, 3,400 is for plumbing devices system, integrated automation for terminal devices for HVAC. That could be for a system that has supplied terminals from a factory that are already done, no contractor involved. 2,536 integrated automation terminal device for electrical systems, 3,700 for communication systems, 3,800 for electrical safety and security systems. So these are all the systems that can be integrated, and each of them have a separate specification. All right, create specifications. Remember that, this is continuing, so oh boy, here they go. Facility controls, facility equipment, conveying equipment, fire suppression, control of plumbing, control of HVAC, control of electrical, control of communication, control of safety and security, control of sequences, automation control sequence, sequences for facility equipment, sequences for all these other systems. So there's a whole bunch of different systems you can look at in the controls. Most jobs never have all of it. They have just the ones they need. Okay, control systems are commissioned the same as the rest of an HVAC system, but have a few special tasks required by the technical CX process. Special tasks. Since every control project is basically designed and built, a more thorough design and submittal review must be performed. Special design review must be completed for the sequence of control. Best practice is to hold a sequence of control workshop between the owner, yourself, the commissioner, the design engineer, and the control system programmer to verify the exact sequence and address any questions for any member of the workshop. Now, you don't need a workshop if it's just a thermostat hanging on the wall, right? But if you have complicated sequences, you need to get them addressed, and a workshop works best. Unfortunately, design engineers have a bad habit of making control sequences very complex. They get these great ideas. They think through it. They're smart people. I wanted to do this, this, and this. But that's a problem, because I guarantee you almost everything you can think of already has an established sequence, one that's been used many, many times, tested many times, and you also have standard sequences from a manufacturer. So we need to make sure that everybody's on the same page. This is where we get problems when you don't do this, and the control programmer looks at those sequences and says, well, I got to do some things different because my system doesn't work that way, or I need some added things. So he'll do it, but he don't tell anybody. And so you get out there to test it and go, this is not working like it's supposed to work. What's going on? Well, I don't know. Well, if you don't have the real sequence, you're going to spend some time trying to figure out what's in the box. So this is not the best process to do it. And if that's still a case, if that process hasn't been exposed and it gets down to operators, they'll have exactly the same problems. So we need to expose everything. So we're going to do a 100% point-to-point control system test performed by the CXP and the control contractor. So we are going to do a point-to-point test. Now remember that we'll talk about it in a second. The control contractor has already done a test, but you're going to do one for commissioning only. Functional system test using the control system performed by the control contractor, verified by the CXP. So first thing first, the contractor does his QC program. Then we come in and do a point-to-point test, and then we do functional test. And we do that on all points. We don't sample. We go through and do all points. It's not that hard to do. I mean, some people freak out and say, it'll take forever. No, it doesn't. It doesn't take forever. My guys, I had 2 guys on the site. We could do 20 to 40 boxes a day, fully commissioning, testing every single point, and verifying calibration. So no, it can be done. It's not a drastic task. Control system sequence of control workshop. Special design review must be done. We talked about that. Required attendees for the commissioning design our design engineer, the control programmer, and the owner's control system operator, and yourself, of course. Optimal attendees can be anybody else, the GC, the mechanical contractor, the control contractor's PM, or any other interested party. Maybe the more operators want to be, it doesn't matter. But you got to have at least the designer, a commissioner, the designer, the programmer, and the owner. You need those three. And why that's important is because a lot of times you'll get into a sequence and the owner will say, wait a minute, stop, I don't want that. You'll say, what? No, I have a standard sequence. We want to use that standard sequence because my guys are real familiar with it. So that's a viable option to have that owner there. Or the owner may say, oh, that's way too complicated. We need a sequence. Or I don't want that sequence at all. Like, let's say you do an optimal start-stop. Well, if the owner is smart, he'll say, wait a minute, stop. I don't want optimal stop. I want only optimal start. And, of course, optimal start-stop is where the system figures out when it needs to start to keep the building in cooling or heating on time. Optimal start is it turns it off early because it knows how long it takes the building to get out of control, so it'll do it early. And the reason we don't like that, because people figure out how noisy the system is. If you're sitting at a desk and working, all of a sudden the air conditioner goes out and gets deathly quiet, you'll be surprised that a system made so much noise. So the owners don't like that. Each control sequence is reviewed, analyzed, and diagrammed prior to the meeting by the commissioner in order to provide key questions. So this requires some work from you. You have to sit down with a sequence, read it, make sure you understand it, ask questions, poke holes in it, diagram it to make sure it's going to work correctly, figure out if it's going to interact incorrectly with other sequences, and then you present those questions at the meeting, getting everyone to understand why you're asking the questions. The purpose is to simplify the sequence to their simplest form so they will be fully functional. Best practice is try to persuade the attendees to utilize the control manufacturer's standard sequence if possible. Remember, simple sequences are more reliable due to being easier for everyone to implement and to keep operating correctly. So not only is it easier for the programmer, it's easier for you, and it's easier for the operators to operate and to keep it operating correctly. So it's a win-win deal. A very complex sequence is not a win-win deal. You know, I've had sequences that are 11 loops deep, almost impossible, and for no reason. You know, the benefit. You know, for instance, I had an engineer once say that, well, I want this reset sequence on the VAV boxes. When the VAV boxes are at 20%, I want this sequence. When they get to 35%, I want this sequence. When they get to 65%, and when they're at 90%, I want this sequence. It's stupid, but that's what he wanted. But we had to talk him out of that because it's impossible. Use ASHRAE Guideline 36 for standard sequences if simpler sequences are not agreed upon. Now, unfortunately, ASHRAE Guideline 36 sequences are very, very good, but not simple. But if you need to standardize on something, there's a standard for you. Commission to publish the full meeting notes and have each sequence listed as a final approved sequence. And they need to be agreed to by the programmer. So now you have that set of sequence the programmer is going to program exactly. So that's what we're really after. The workshop outcome will be that all parties agree at the same sequence and no one will need to guess at the final program sequence. The workshops work really well. They take a few hours. It depends. It may take 4 hours if it's a bigger project. But at the end of the day, everybody comes out saying, okay, that was a valuable process. And by the way, those workshops can happen on any kind of control system, process control system, fire alarm control system, security system, because they all have the same issues. Okay, activities during construction are the same for the HVAC, submittal reviews, control drawings, control component submittals, graphic plates. Now remember, for controls, to do a full point-to-point test, we want to do it from the graphic plates, so the graphic plates must be done. Not, you know, in the older days, the way this worked is the mechanicals, all the contractors built a building, and when they were done, the control contractor was done and everything installed. He then started his graphic programming about that time. So many generals used to jump me and said, you know, the last job, we weren't finished with the control graphics until 6 months after occupancy. That can't happen. We need them early. So what you want to do is you make sure the specification calls for the control contractor to include a typical graphic plate for each type of system. Put one in for a typical VAV box for heat, one for non-heat. Put in one for a typical constant volume air handler, put one in for a typical VAV air handler, and so on. And that way, the owner gets to see the graphics and says, okay, that looks good, I like it. The designer gets to see the graphic and says, yes, that's got enough information on it. And you as a commissioner get to see it and say, yes, it has the right points for me to commission. So those are very, very valuable. If the control guy doesn't do that, I tell you, the sad part is it's stupid because it costs him so much more money. If you have 100 VAV boxes on a job and you don't have a request to actually provide the graphics early, and you work through and you do all 100 graphics, you get done, and the owner looks at it and goes, well, that's not what I want. That doesn't have the right data on it. Now he's got to redo 100 graphics. This is not pretty, but it can't happen if you don't have approval. So you need to make sure that the graphic plates are approved. Final sequences of controls, control PFD pre-startup inspections, control PFD startup, kickoff meeting. So this is a general commissioning kickoff meeting, site observations, functional performance test. So in all these different things, these are the normal process of controls, and the commissioning logs. Performing control submittal reviews. So you're going to perform the review. Components and devices are in compliance with the specification. That's what you're checking. Control network architectures in compliance with the specification. Panel drawings include faceplates, panel device locations and cable management within the panel. Panel drawings include control diagrams and wire tag device names. Control diagrams include wiring diagrams for both control and power circuits, and include device lists with model numbers and components. Submittal includes a typical graphic for each type of system, showing the control and data points to be displayed. Submittal includes valve list, including size, valve type, valve CV, actuator type, model number, and actual pressure drop of the valve. Submittal includes control damper list, including size, damper type, actuator type, model number, and damper size. As part of the process, each contractor has a QC program, including the control program. Now, the control contractor has a little bit more detailed QC program and a little bit larger QC program. The control contractors have one or more trained, experienced technicians who are assigned to be a part of the commissioning team, who are responsible for the control system quality control program for the commissioning process. The individual shall bear responsibility for the contractor's support and coordination of the commissioning process of their work, which shall include creating their system pre-functional tests and check sheets. Now, normally, this person's the project manager for the control team. That's normally who it is, but it might actually be a programmer, or it might be a lead technician, but normally it's the project manager. Creating their system pre-functional test sheets. Most manufacturers have these already standard, so you don't need to worry about these. So these are normally standard ones. Perform their pre-functional tests, so they normally perform all their pre-functional tests themselves. I don't normally observe those. Assisting the commissioner with corrections or compliance issues with the PFD tests. So now, a lot of process commissioners, they observe the control contractor doing these pre-startup, pre-functional test check sheets. The reason I don't do that is because what the control contractor is checking, he's loop checking. He's checking his loops. What he's checking for is to make sure he's got them connected to the right points and the polarity is correct, and they're getting the right signal. He's not actually going clear to the graphic. He's just doing that little field piece to make sure he's got it installed correctly, which needs to be done and is correct. So that's a good thing. But it doesn't do the whole system. We're actually going to do our point-to-point test from the control point clear to the end device. And the reason is many systems, you have a database and you have to manually connect the point to the database. That's a process where you could have air handler 1 start-stop connected to air handler 2. That's why we check clear from the point. We don't do it just within the control with the laptop. We actually want to see the graphic involved in that. PFDs are either installation inspections or startup reports that are normally created by the control contractor for each control on the project. The contractor creates the PFD check sheet and he performs them. The installation check sheets verify the correct piece of equipment is installed in the correct location, that it is installed correctly, and that it has adequate access for maintenance and operation. Once the installation is verified complete, it is ready for startup. The contractor creates the PFD check sheet and performs them for startup check sheets. Documents the startup process by recording key startup parameters in the system. Once the startup is complete and verified, the system is ready for point-to-point testing and functional testing. Now, what happens here is the control contractor, his startup is basically making sure everything powers up, downloading the programs, testing the programs, make sure they work, make sure everything's communicating. That's his startup process. So, these represent the control contractor QC program. See the training section Cx-7 for HVAC system pre-functional test. It'll show you some examples and that kind of thing. Site observations. During the course of construction, startup, and testing, the CXP performs the observation to verify construction activities are in conformance with the design and will not impact the system performance. These are important. Site observations may include power and control cable and raceway installation, control panel and controller installation, sensor and control device installation, controller and graphic programming, controller system installation, and startup tests performed by the contractor. So when you're doing a site observation, cable and raceway is kind of a spec item to make sure that they've been according to spec. And if it's cable only, then you have some quality issues to make sure it's not getting RF interference. Control panel and controller installation is kind of an important one to look at to make sure they've done that correctly. The sensor and control device installation is absolutely required. This is the most important one here because if they've installed the sensor incorrectly, it's not going to do its job. And then control and graphic programming, we'll probably do that as we're doing our point-to-point test. But that's what we should actually look at. You can see Cx-2 for system site inspections to tell you how to do site inspections. So observe percent complete by system area. So when you walk through a job, you want to make sure, well, what percent completed were you? So you can kind of address that in your next commissioning meeting where we're at. A lot of times a general contractor will not be aware of how far they are because you can't tell sometimes, right? They've hung all the controllers, but what have they done beyond that? A lot of times a general contractor cannot tell. So maybe a general contractor said, we're going to start up this job next week. And you go, I don't think so. They're not ready. So you need to be able to look at things that he may not be able to see. Generally inspect the cable installation, conduit hangers meet required specification. Observe control panel installation. Observe control power has been installed. This is important because there is a code requirement that you can't mix voltages within a panel. And control contractors violate this all the time, and you should prevent them from doing that. Observe controllers, control device installation. Like here's a typical panel. This is, of course, here's the control diagram. Here's the point list to list what the wires are, the wire tagging notes. Here you can see they show where the controllers are mounted, where the devices are mounted. It might be some controllers or relays mounted. Here is a power supply, and here are what we call gutters, and these are wire devices. They route the wire around the panel so it's just not a big mesh of wires. And here you notice that this transformer is mounted inside the panel. Well, that's okay as long as it doesn't have exposed wire at a different voltage. So if this has all got 24 volt AC in it, and this is 120 volts coming in, it has to be in a metallic separation. It can't be in the panel. So what we did a lot of times is we'd mount this transformer out here with a bulkhead fitting going through to this power supply. So basically the transformer was outside the panel and the only wire in here was a 24 volt wire. But if you put it in here, this has to be in conduit. Now a lot of times I'll see them try to put the transformer down here. That's absolutely a no-no, and bring 120 volt raw wiring down to this. It should never ever happen. That's against code, number one. Number two, it provides opportunity for radio frequency in your panel. It should never happen. This also shows pneumatic tubing coming in from pressure sensors or whatever, and how to use bulkhead fittings. It shows how your conduit should interact. It doesn't matter where, but this is the process. And this is a typical control panel, and this is what you should be looking for. These are sensor inspections. Here's a regular temperature sensor. They should be on a plate. This sensor should be mounted on a 4x4 box plate. It should be screwed to the duct so it's stuck in. It should just be a bead sensor stuck in the duct. I've seen that. This is a typical sensor for a low temperature sensor, like a freestat. So if this is a capillary sensor, the instructions say it should be mounted horizontally. It should go through every square foot of the coil. So a lot of times you get on a job and you see these go like this, or you see them all wrapped around a conduit. None of those are correct. They need to be installed according to the manufacturer's instructions. The reason is a capillary has liquid inside of it and gas, and it will, if you do the V-shaped one, it will the fluid will all go to these dips, and it will no longer read correctly. And then I have a lot of contractors say, well, man, 20 foot's the longest one I get. I can't get through the coil. Then you have to install more than one and wire them in parallel or in series. So basically, you have two of them. So control contractors don't like this. It's a big job. It's the way it has to be. These are pipe sensors. Here's another sometimes comical ways. Normally you want to see a pipe sensor installed in a pipe like this with a weld inlet. The pipes put a pipe well in it, and it's supposed to go to the center line of the pipe. And then we put some thermal paste in it, and the sensor goes down into that thermal paste, and it will correctly read the water temperature. What do I get? I get contractors say, well, this is only 1 inch pipe. I can't I can't install anything like that. So what they'll want to do is they'll take a T, and they'll put a bunch of, this would be a straight through T, and they'll put a bunch of reducers and put the sensor here so it's not to the center line of the pipe. That doesn't work. So you need to explain to them you can put it at 45 degrees, you can put it in an elbow heel, or you can put it in a T like this, and it will be in the center line of the pipe, and it'll fully see what it's getting. You just can't stick it out of the water. Then we'll get the argument, well, they don't make welds that size. And that's a lie. They make temperature welds in 1 inch increments from 4 inches to 96 inches. They make a well. So you just need to not, a lot of control contractors use small wells, and they only have them in 2 inch, 4 inch, and 6 inch sizes, even for a 12 inch pipe, which is not correct. So you need to catch those kind of things. Also, we have somewhat of a condition of how do you actually test a sensor on a water line. You realize the sensor's in there where you're going to test it. You cannot use a clamp sensor because the wall will, the temperature of the wall will not be the temperature of the water, and that leads to inaccuracies. The right way to do it, which I only normally see on industrial, is you put a sensing well, a measurement well next to the actual measuring well. So this is a test well. And what you do is you just have this with a cap on it. When you get there, you move the cap and you stick your test instrument down here. Now you're reading exactly the same as the controlling sensor. But without that, you got to get clever. And what we normally do is we read this and then we pull it out and put ours right back in there quickly and read it again. Or else, if there's a drain right close, drain some water out in a bucket and take the temperature in the bucket. I mean, this is challenging to find exactly what the temperature of the water is. But you can do that. And then, of course, pressure sensors. Remember, pressure sensors may be sensitive to overpressure, so they should have an equalizing manifold on them. And then they also should have a pigtail on it to prevent vibration from affecting the pressure sensor. And this is general cable. Normally, if we're running free cable, which means not in conduit, we want them to be up high in the structure. We don't want them tied to ductwork. We don't want them tied to electrical conduit. We don't want them tied to cable racks. Now, that may sound funny, but cable racks are the communication people. If you put your LAN wire in a cable rack, it will get cut out because the cable guys are trying to keep track of the hundreds of cables they got in there. And if they see a spare one that they don't like it, they'll get rid of them. So this is for your own benefit. This is for the control contractor's own benefit to do this. And of course, always never put them over the top of light fixtures. LEDs and fluorescent bulbs may have transformers in them, and they will put radio frequency on the line. So if you have a group of cables, the right way to do it is they twist them together and put wire ties on them so they actually become together so they're not loose. If they have between floors, a lot of times we'll run a conduit in an exposed space and put the cable between it, or else we have conduit going from floor to floor, or we use thermostat drops where we come in this way, or the main LAN may all be in conduit. It depends on the specification. And a lot of times this conduit is painted blue. Normally it's blue for controls. That's so they can identify a control conduit from someone else's conduit. So point-to-point test. Graphics must be 100% complete for the tested controllers. One technician in the field verify the system reaction or status. One technician at the graphics station operates each point or verifying status of each point. One control technician to assist in operation of software or program if needed. And here's the process. So you have a technician with a calibrated instrument tests the sensor, and someone reads on the screen and says, yep, that's exactly the same temperature I have. If not, then you record the variance. What is the variance between the two? And if the variance is very large, then we're going to do an offset. And I'm not going to explain that in this video, but the offsets, there's another video that will explain that to you. Binary and digital points, command points, and verify that action and verify the status is correct. So you say start, stop, or open and close it, and make sure it actually does what you commanded it. Analog sensors using a calibrated instrument measure the instrument variable and compare it to what is shown on the graphic screen. Actuators command the actuator field verify its position and reaction, and verify its status on the screen. So it's really simple. This doesn't take long to do. Now, sometimes if you're doing a VAV box, they can be really, really slow. So it's good to do a whole bunch of them together. You know, so you command 20 boxes to do the same thing. You walk around to make sure they've done it. It's faster that way to get through it. What is tested? Verify that the correct point is connected to the correct device and its polarity is correct. Digital point inputs, status input switches, sensor calibration verification, digital point outputs, relays, two-position dampers or valves, actuators range verification, graphic point matches sequence requirements. When you're doing sensor calibration, you only need to do sensors that actually control something. If you have status sensors out there, I don't see the need to calibrate those, unless the sensor is going to be critically important for the exact temperature or exact pressure. If they're controlling, that they need to be calibrated. If they're not controlling, status is just general, something is off and on or it's generally working. You don't care if it's a half a degree off or whatever. And then actuator range verification is making sure the actuator goes full closed. Actuator should go full open, but that's not near critical. If an actuator goes 99% open, the flow will never notice. If it doesn't go full close, it will destroy the valve. So full close is very, very important. And you do that by adjusting the linkage. Functional testing. Now, functional testing is what separates the men from the boys or the women from the girls when we're trying to do commissioning of control systems, because that's the key thing. The commission provides the FBT test script to be used to prove functionality. The CX team will observe all functional tests. Normally, the functional performance tests are operated by the control contractor. Functional tests may be manual tests where the CX team observes and documents each steps or action and reaction of a sequence of operation of control. Automatic trend functional tests utilizes control data trends to document and prove functionality of all complex control sequences. A successful FBT means the system is ready for occupancy. So you can see the training Cx-7 for functional test. And basically the way we do these automatic trends is the control contractor sets up the trends you ask him to, launches them, observes them, and when they work correctly, documents them, sends them to you so you can look at them. Or you're normally there. I've had a problem of giving them to the control contractor to do all these trends and send them back to me. They send them back to me, most of them have failed. I said, why did you send me all these failed sequences? It's because they don't know. They don't understand what's a success and not. So you need to be helpful there. Commissioning issue log is no big deal, just like everything else. Describe the issue, what it is, the discipline, resolution for contractors, respondent's name and company, date of response. During completion of one of the activities, the CXP shall review the O&M manual. O&M for data device warranty meets the OPR. List of required programming software, list of required programming tools if required, programming instruction, maintenance instructions, troubleshooting guide, parts list. Identifies who to call for service or spare parts. That may sound funny, but I've done many jobs where they don't ever tell anybody, so how are they supposed to get service? Owner training. Now this is actually very, very important. The CFC, the commissioner shall include training documentation as follows. Training document records that include data times and attendees of each session. Final copies of approved O&M manual. Final as-built submittal drawings. For controls, this is absolutely required. Sometimes there's a lot of changes to control systems, so we need them documented because the operators need that data. So we need to make sure that it's included in this final documentation. Approved submittals, shop drawings, and manufacturing installation instructions. Classroom topics shall include what is covered under warranty and what is not. Suggested service contracts. Review how to obtain service and programming assistance. Review how to obtain service parts. Who to contact for technical systems. Review offered factory system training and programming training. Controls training session shall include review of the system architecture, review how each type of control is programmed and where backup program is located, review the programs are modified and downloaded, instruct on how to start up the system, instruct on how to test and maintain the system, instruct on how to recover from a failure, instruction on troubleshooting techniques for common problems, instruct on how you set up passwords and their management, instruct on how to set up and modify schedules, instruct on how to set up, acknowledge, delete alarms, instruct how to set up and run data trends, review how to properly back up and archive programming, hold a question and answer session. These sessions are important. A couple of things. Try not to do 8 hours straight of programming training. When an operator sleeps through a session, it's not a good idea. So keep it to 4 hours to keep them sharp, have it over more days, but pay attention to they need to actually have this data. I've seen workshops where you did a training workshop and half the crew slept through the deal because they were night crew. They brought all the crews together for this, so you have to pay attention. It has to be good training. Best practice is to hold a classroom training session with a hands-on training event where operators start, operator shut down the actual system or a piece of equipment. So they need to learn it in a classroom setting, and they need to go out and play with it. It's really important. The report has an executive summary including final approval of control system and its operations, copy of the final issue of the log indicating all deficiencies and recommended corrections, copies of contractor PFD for both inspection and startup, copies of 60 point lists, copies of the functional tests, copies of final updated drawings. System manual is have a facility guide for the controls. It tells them how to operate the controls. Includes programming manuals for all software. And in this facility guide, you need to kind of tell them what's important. You need to understand and tell them that the reset sequences are critically important. Don't turn them off and don't blow them out. Because a lot of times when the system's not working, they'll assume, well, that reset sequence is doing it. I need colder water, so I'm going to blow that out so I get colder water. But that's not the root cause. That's a symptom, and they need to find the root cause. Key equipment submittals, copies of approved O&Ms, copies of PDF drawings. After completion, any tests that were deferred due to weather or other operating issues shall be performed during the deferred test. All functional tests should be documented as per technical functional test requirements defined by the commissioning team during the acceptance testing. Any issue will be added to the final issue log for resolution by the contractor. A warranty report. Prior to the end of warranty of the project system, the commissioner team shall view all completed and outstanding warranty issues and create a warranty issue report. The commissioning team shall analyze these warranty issues to determine if there are any underlying causes from unresolved construction issues. So this sounds complicated, but it's not. The easiest way to do this is contact the general contractor in about 10 months. Tell him you need to do a report to finish your project. And could you get a copy of all the warranty items that he's processed? And he'll download. He just downloads a list. And it'll have a lot of things maybe you don't want to see, like building enclosure, parking lots or stuff. But he will have a complete list of everything. You just need to include those in your report. And then you need to talk to the owner about any current issues he's having. If it's nothing, you're done. You update the CX report to include all those things you've done, and that's it. You're done. So control testing commissioning is not difficult. It has a lot of testing involved, but it's where you really make a difference. If you don't do this process, you will not make a difference on the project. And that's what we think commissioning is all about, is making a difference. So thanks for watching. I hope you had a good day. I'll catch you on the next one.